Okay, this afternoon I want to talk a little bit about wild, wild weather. And essentially I'm going to talk about the Ice Age, which I believe and ICR teaches occurred following the flood, and in fact was a major consequence of the Genesis flood. And I'll tell you why, and it's a very exciting thing, and I have some, I think, very interesting graphics to show you as well. But I also want to talk about three other topics. Actually, on this presentation, I could spend about 3 hours talking to you. I have hyperlinks built in because it allows me to skip a whole bunch of it, depending on the audience I'm at. And I thought today, though, I would give you a little bit of information on 4 topics very quickly. The vapor canopy, some of the latest findings on that. Then the Ice Age, which I call the Big Freeze. And then some global climate modeling using computer models on PCs, believe it or not. And then a little bit of the latest work of one of my students on hypercanes, having to do with giant hurricanes that probably formed on the surface of the earth right after the flood as well because of the hot temperatures on the ocean surface. The vapor canopy model, as many of you have asked, and I've been putting you off all week here to give me a chance to tell you a little bit about it here today, has been around for many years, and the vapor canopy model has had its ups and downs. It's a concept that at the time of creation, God separated the waters from the firmament, or the atmosphere as we believe that is, from the waters were separated from beneath this firmament and from above the firmament, so that we suggest that there was a layer of water placed above the atmosphere, which protected life on the earth, and may have been an explanation for some of the longevity of the patriarchs, if there was enough water up there to produce higher pressures. It explains a number of things, such as why there were no rainbows until the flood, because at the flood this canopy would have collapsed, allowing the light conditions to be different and rain to form and a number of other things. The nice thing about the vapor canopy is it explains a whole bunch of statements in Scripture, but it is not an explicit statement in Scripture. You have to understand this is a model. It's a theoretical construct that was put together from various ideas and so on. And about 30 years ago, let's see, has it been now? Yeah, 30 years ago, Dr. Joseph Dillow did his work at Dallas Theological Seminary under Charles Ryrie, and his dissertation was on the vapor canopy. If you've never seen that report, it's called The Waters Above, and it suggested a model. It went through and talked about all the history of the vapor canopy and the history of the flood and that sort of thing, justifying such an idea. And he worked with me when he was a student there. I just finished my doctorate at Colorado State University. Dr. Henry Morris referred him to me, and I helped him while he was a student at Dallas Theological Seminary, one of his advisors on some of the technical aspects of that model. And so when he published that model, it had some of the ideas that I had worked with him on. Since that time, Dr. Dillow hasn't done a lot of work in that area because he spent the remainder, or the last 30 years basically, in a missionary operation behind the Iron Curtain to the Soviet countries. And then about 12, 15 years ago, went to Hong Kong and is now doing a similar ministry into China. Basically biblical education by extension, teaching pastors in these countries and seminary training. Excellent ministry. So he hasn't done a lot on that area in the last few years, but he's maintained an interest in it. But I've been the primary one to continue that research because I was intrigued by it and had the expertise to continue working with it. So several of my students have done work on it, and I have as well. Unfortunately, we found some problems with the model. It's such an attractive model, I can't give it up though. It explains so many things if it would work. The big problem with it is though, when you put a lot of water vapor into the atmosphere, say 40 feet of liquid water in vapor form, like Dr. Dillow suggested, you get an incredible greenhouse effect. I mean, we're talking about 600, 800 degrees Fahrenheit at the surface of the earth under such a canopy. So I've been struggling with that, trying to reduce that heating by all kinds of various techniques, and so far have not been able to do a complete solution to that. It just stays hot. But I was about to give it up about a year ago, or a little more, a year and a half ago, and I decided to do one more effort at this model, and if it didn't work, I was going to quit working on it. I had many other things I needed to do. But I did discover, or not discover so much as suggest one other possible scenario, and it has allowed me to have cooler conditions. Unfortunately, the suggestion I am making is maybe even more controversial than the vapor canopy itself, and it has to do with how much heat output the sun has. So I just kind of moved the problem from the Earth to the sun. Let the solar scientists solve the problem, right? Well, so I'm just suggesting as a possibility. This is not a solution, but it is an interesting issue. Let me make a few comments about this, and then we'll go on to the Ice Age. Okay, basically the model is similar to the one that Jody Dillow had 30 years ago in terms of a two-layer canopy. The lower layer is the atmosphere. Well, first of all, the horizontal axis here is the temperature from 30 degrees to 100 degrees centigrade. That means 30 degrees is about average, a little warmer than average temperature on the Earth today. 100 degrees centigrade is the boiling point of water. The vertical axis is the height up in the atmosphere from 0 to 50 kilometers. At any rate, if you have a water vapor canopy resting on top of the Earth's atmosphere, it would squeeze it down and make it much shallower, and then the water vapor would be above. With the kind of temperature distributions we assume here, you would end up with a massive inversion condition, which leads to air being warmer the higher up you go, light winds, no precipitation, very few clouds, no rain, no rainbows, and things like that. So it has a very attractive feature in terms of the way the Bible talks about the pre-flood world. Anyway, that's the basic assumption. That's pretty simplistic also. Obviously, you'd think there might be some mixing between that upper layer and the lower layer, and it'd go away fairly quickly. It turns out it doesn't. It persists fairly well, as long as there's not a lot of strong winds, which there probably wouldn't be in those kind of conditions. Okay, well, given that kind of a model then, what kind of temperatures would you get? We started with a vertical temperature distribution that was uniform at 170 degrees Kelvin, which is about a minus 100 degrees Fahrenheit, very cold. You see that here in the left part of the image. And then allowed solar radiation to warm it with time. And these intervals, each one of these lines is like, the first one is at time 0 days, then 10 days, 20 days, 40 days, 80 days, 160 days, and 320 days, and there's another line there that you can barely see, 640 days. And you can see it basically stopped warming at that point, so it came to what's called steady state conditions. But you'll notice the problem and this is with a relatively minor canopy. This is one with 10 millibars of water vapor in it, which is about a foot of water. A foot of liquid water in vapor form on top of today's atmosphere, and the temperature at the surface of the Earth comes out at 400 degrees Kelvin, which is almost 100 degrees centigrade above the boiling point of water. In other words, it's extremely hot on the surface of the Earth with this relatively minor canopy. So water vapor is a really good greenhouse gas. Well, that's where my student Dave left his model, and he had some suggestions or recommendations about what we might do, but it was a little discouraging. He tried this at a number of different canopy depths, and he had a final surface temperature of around 300 and some degrees Kelvin. If you put more in it, it got hotter and hotter until you got up to as high as 500 degrees Kelvin, extremely hot, and probably would increase slightly more than that, but with a mass of a canopy equal to what Dr. Dillow had suggested of 100 millibars, or about, let's see, is that 100? No, that's 1,000 millibars, which is about the equivalent to the mass of our atmosphere today. So it's extremely hot, and that was the basic problem. Well, I've done a number of other models. I've been able to fix it a little bit. I've convinced up to as much as 3 feet of liquid water with some really strong adjustments so that the temperature wasn't so cold, or it wasn't so hot. But until this last year, I didn't have any way of really getting that temperature down at all. And what I'm suggesting at this time is possibly if, for some reason, the radiation coming from the sun is not as great as we know it today. By the way, this is a perfect example of uniformitarianism. We've been assuming that the solar radiation in the past has been the same as it is today. That's uniformity, right? So it occurred to me, why don't I make some adjustments there? I don't know why it would change, but let's just assume it did. And so I'm now looking at variation all the way from 1% up to 100% of today's radiation. Now, whether that radiation would be reduced because the sun is not putting out as much, or because the Earth's atmosphere is reflecting more from the top of it so it doesn't get down into the atmosphere, because once it gets in, then it gets trapped and there's all kinds of radiation problems. Or maybe there was dust between the sun and the Earth and for some reason and it couldn't get to the Earth. Or, let's see, what was the last, oh, this is a really heretical idea. Maybe the radius between the Earth's orbit around the sun was greater than it was or is today. That means it's further away. For every time you double the distance, you get 1/4 as much radiation per unit area on the Earth. So I've explored that possibility. Now that throws all kinds of kinks and other issues, but you know, that's what a theoretician does. So I've not really addressed why the radiation might be, but I've explored what it would be if it was between 100% of, like today, all the way down to 1%. Here's an example of that same type of calculation I showed before with a temperature here in degrees Kelvin, height in the atmosphere, starting with a temperature of 170 degrees, completely uniform. And the reason we start with that, by the way, that's the way it has been done in the literature, in the conventional literature, so we got some comparative ways of looking at it. And it also doesn't put any bias in there. If you started with some temperature that was close to one of these, someone could accuse you of biasing the calculation. If you start with a uniform distribution, very cold, and let it warm up, or in this case, cool off, then whatever it comes to equilibrium at is what you're going to find. So here's one in which we have 1% of the solar constant, that's the radiation coming from the sun today, and it cooled off with time, and this is at the poles, by the way. You gotta worry about latitude, look at the poles and the equator, and you find after 1,280 days, it comes to equilibrium here, but the temperature at the surface of the Earth is like 140 degrees Kelvin. Extremely cold. I mean, that's colder than anything we have on the Earth today. And it turns out that if you do have that, you are going to be worrying in the upper part of the atmosphere where it's even colder, way down here close to 70 degrees Kelvin, that you're going to start condensing out the oxygen and the nitrogen, not just water vapor. So you have to worry about the whole atmosphere collapsing. This began to remind me of a science fiction story I read when I was in high school. I became a scientist because I read science fiction. They weren't quite as evolutionary in those days. It was more, well, they were space aliens and things like that, I guess. But there was a story, I don't even remember the name of the story now, but I remember this guy was on a planet and it got so cold that the whole atmosphere fell out and it was about this thick and it was in solid form. And he was breathing in a cave to try to survive until a spaceship came to rescue him. Well, that's what this reminds me of. We got an extremely cold environment where the whole atmosphere collapses. Well, you can look at the other situation at the equator where it's going to be warmer. And in fact, here's what it looks like with 100% of today's solar constant at the equator, starting with the same 170 degrees Kelvin, and it warms. And again, we get back to what we found before, approaching 400 degrees Kelvin at the surface of the Earth. These are times from 0 to 1,280 days. And you see it comes to equilibrium. Okay, well, let's look at it as a function of solar constant. Assuming you start with these are equilibrium values now for 1% of the solar radiation at the poles, and it has a surface temperature like 140 degrees. At 100%, it's up around 240 degrees Kelvin, which is still about minus 30 degrees centigrade. That's quite cold at the poles, but you've got quite a range there you could play with. At the equator, this is 1% up through 100%, and you notice at the equator, at 100%, again, you've got those high temperatures, but you also got colder temperatures even at the equator. So now what I'm finding is we have the range to play with, both at the poles and at the equator, and now I could potentially increase the amount of mass in the vapor canopy and still retain temperatures that might be livable. So that's where I'm at in that research, and I wanted to report that to you. Here are the conclusions from that. The solar radiation may have been less in the past. It may have been as much as 25% or less if some of these models are valid. A vapor canopy may have actually been needed in order to keep the atmosphere from getting too cold. And healthier conditions may have existed if we had enough of a mass in the canopy to increase the pressure at the surface. So basically what I'm saying is the vapor canopy theory is still alive. It's not exactly well, but at least it's alive. So I'll keep reporting. as we continue to do research on this. I realize that I may be dangling you out for a few years because, you know, some of you said, I'm going to give up on that. A lot of people said, that's not a legitimate theory, it's not working, so we'll give it up. I wanted to keep working on it. I was about to give it up, but I'm going to keep going a little bit. Anyway, that's where it's at, okay? Let me make a real quick comment on helium escape. I have a whole presentation on that, but I don't have time for it. Let me just say that the helium escape has a new phase. It turns out that the conventional scientific community was paying attention when we dealt with the helium escape problem in the Earth's atmosphere and the argument we used for a young Earth. And they couldn't handle that. So they went back and they spent several years and they claimed to have developed a new magnetohydrodynamic model that would explain loss of helium, not just simply thermal escape from the Earth's atmosphere, but open magnetic field lines where the helium can escape out near the poles as the solar wind comes in and sweeps away the helium. Now that model is much more than thermodynamic. I'm primarily a classical thermodynamicist. That's why I went into atmospheric science. So it's going to take a little bit of my ability. It's going to take a lot more than my ability currently to be able to study that, but I've got to go back and hopefully I can get to this year and study it because it also has implications for rate. And so I've got to go and study that and see whether that's a legitimate model. It's completely theoretical with a few observations here and there from various space measurements that they try to confirm that model with. So it's again, we've got to go back and look at that again. Science doesn't stay stationary. Okay, here's one I want to spend a little time on, a creationist ice age. Now, many of you may have heard some of this information. You may have read a few of my reports. Some of you may have actually heard my presentation, but I don't think I have spoken to an audience that would include most of you. Basically, in a nutshell, the Ice Age, we believe, is a consequence of the Genesis flood. We believe that the Genesis flood was such an energetic event that there was tremendous quantities of heat that were released in the process and were left in the waters of the ocean when it returned to the sea, when it went back into its seabed. And because of that, there was a giant El Nino effect. Because when the surface temperature or the ocean temperatures are warm enough, you get hurricanes, you get tremendous evaporation, and if you have a lot of evaporation, you're going to have a lot of condensation, precipitation on the continents, particularly in the polar regions and in the mountains. And we believe for up to maybe 1,000 years, there was this process going on, which created the Ice Age very quickly, and then at the end of that, it deglaciated very quickly, and the climate then transitioned into what we have today. That's the idea in a nutshell. First of all, though, I need to convince you there was an ice age. One of the things we have a tendency to do is when we have an idea that's developed that we think is going to be a problem, we tend to go into denial. And that's what many of us did with the Ice Age, or do. That is, well, there never was an ice age. So first of all, I have to convince you that in fact there was an ice age. I'm going to do this from evidences of mountain glaciers, continental ice sheets, drumlins, moraines, kettles, striations, and erratics. Okay, here's an example of past erosion in mountains where there were ice sheet, or actually glaciers in the past. By the way, a glacier is layers of ice that form in mountains and move down the slopes into the lower terrain. Ice sheets are layers of ice that are on more flat terrain, and they move because there are variations in the thickness of it. There may be regions where the precipitation falls much more greatly and it has mounds in it, and because of the difference in the thickness and the weight of that high spot, it moves the ice out sideways. Kind of like some of you that make taffy. You know, you make the taffy on the stove and you pour it out onto a slab of marble or into a pan or something, and it just kind of floats out. That's the way ice sheets do, only much more slowly. The ice is plastic. At any rate, in the mountains, when ice sheets formed, or glaciers formed in the past, they moved down the mountains and they eroded the underlying surface. Here's a good example of how ice erodes the tops of mountains. And there are many places that you'll see this in mountains, and particularly where the peaks become very sharp and the stuff is slumped away. Some of those can be actually rock slumps and avalanches, but much of it could be ice and snow that occurred during the Ice Age period. We find that all over the world. And by the way, these glaciers that we believe occurred more widely and to much lower elevations than they occur today in mountains. There's glaciers today on the mountains, but they are much higher. They extended much lower in the past. They can occur down even in the tropics. And there's evidence right even in the equator in Kenya that, for example, where there were glaciers that extended much lower in the past. So it's a worldwide phenomenon. Yosemite National Park is a good example of where glaciers came through. The valley to the left, which comes by Half Dome, the ice at one time filled that valley up to these layers here and maybe even higher, and ground away the cliffs on the side, leaving them vertical, and that's why we have these beautiful waterfalls today. The face on Half Dome was probably knocked off by a glacier coming down the valley in Yosemite. Here's an example of what are called striations. This is in Newfoundland, where the ice sheets up in the northeast part of the United States and off the coast into Newfoundland and that area, off of Canada. These ice sheets were so heavy as they moved out to sea with rocks and hard material under the ice, scraping across the solid rock below, it left these distinctive scrapes called striations. And you can look at them in more detail up close, and they're very distinctive. And you can map where ice sheets and glaciers have moved in the past by those alone. Now here's what are called erratics. This is a boulder that was left in this position by movement of ice sheets, which actually covered this whole mountain area. And the boulder was resting on top of the ice and snow, and as it moved through, it worked its way down through the ice, or at the end of the ice age, the ice all melted, leaving this boulder in that position. Now you find these all over the world, around mountainous areas, but the thing that makes you reasonably confident it is due to the ice age is because this boulder is made out of material that's different than the material that it's resting on. And in fact, this one came from a mountain over 50 miles away. That particular kind of material came from the mountain 50 miles away. Those of you that may go to Yellowstone, in fact, yeah, I told you there's a brochure on Yellowstone. We'll be going in September to Yellowstone, taking a tour there. There is a boulder or an erratic in Yellowstone National Park right near the Yellowstone River, right below the falls, which we go and drive by. And it's about the size of your living room. And it's in among the trees, and it was moved there from the Beartooth Mountains about 30 miles or 40 miles to the northeast of its location. It as well was brought in there by glaciers. In fact, Yellowstone National Park, if you've ever been there, Yellowstone Lake and the whole central part of Yellowstone National Park was buried about 4,000 feet deep in ice and snow. The mountains to the north part of Yellowstone and to the south of Yellowstone both were covered completely to the top and above with ice at one point in the past, based on erratics and striations that are observed in the park. This is an example of what happens when an ice sheet or a glacier comes in and it produces features on the ground called moraines. It's kind of like a bulldozer as it's forming and moving across the ground. It actually picks up some of the soil beneath and rocks, and maybe even the weight of the ice on the ground actually depresses the ground under the ice sheet and therefore pushes it out from under it out ahead. As it melts back, it leaves all kinds of particular streams, and it may leave lateral moraines, as they're called, similar to end moraines, but along the direction of the movement of the glacier. It leaves kettle lakes, these little holes. What these was where large chunks of ice were left behind as the glacier or ice sheet retreated, and as soil moved in to fill behind the glacier, it couldn't fill in where the big chunk of ice was, and then later, when the ice melted, it left this little lake in there. You're probably from places in the country, many of you, where there are what are called kettle lakes. That's how they're formed. Canada has lots of them. They're all along the east coast of the United States and many places. There's a number of other features like that. Here, for example, is under an ice sheet or a glacier, where when the ice melts, it forms rivers and melting regions in the ice, and water percolates down through the glacier, sometimes in large columns, like a vertical waterfall with a big funnel up above. If you've ever flown over a glacier or seen pictures of them, they get this magnificently blue water where the ice is melting on top and it's resting on top of the ice. that's really a reflection of the sky above. The water's not literally blue, it's the sky that you're seeing, but it's got a white background underneath it of the snow, and it makes this brilliant blue. Beneath the lake, maybe waterfalls or these areas where the water goes down below. The rocks and soil is collected underneath and forms particular features called eskers and various other features that you can associate with ice sheets and glaciers. Well, taking all that evidence and trying to figure out where these ice sheets and glaciers occurred, here's a distribution that's generally accepted as to where they were in the northern hemisphere. And you'll see here that the ice sheets, anywhere from 2,000 to 3,000 feet, maybe up to, estimates have been as high as 6,000 and 8,000 feet deep, cover all of Canada, the northeastern part of the United States, and down through the midwestern part of the United States. We're actually south of where the glacier, or the ice sheets were here in this part of Indiana, but a little bit further north, that was all covered with ice sheets. In fact, you can actually tell just simply by the type of terrain. You go north of here, and you know where all the cornfields and the wheat fields and the flatlands of Indiana, Ohio, Illinois, Missouri, Iowa, all of that was under the glacier at one time, all the way up through Canada. Where you find the little rolling hills and foothills down in the southern parts of these states, that's where the ice sheet stopped. And it didn't plow down or flatten this part of the country. The ice actually extended down into the northeast, clear down into New York City. New York City had up to 2,000 feet of snow and ice on it during the Ice Age. Central Park has rocks in it that the ice moved over, leaving striations right in the middle of Central Park. Out in the western United States, it covered in the Puget Sound area. The whole Puget Sound was filled with ice. In fact, Seattle-Tacoma Airport is sitting right on top of an a lateral moraine. If you ever wondered about that peculiar shape there, it's maybe 10 miles long and about 1.5 miles, 2 miles wide. They put the airport right on it, north-south, right on top of that lateral moraine. The Puget Sound itself was completely full of ice, all in through that whole area there. And the mountains all along the coast here were covered with ice and snow. During the Ice Age, because all this water and snow evaporated from the oceans and ended up on the continents, the sea level worldwide was as much as 300 or 400 feet lower than it is today, opening up passages across the Bering Strait from Asia, allowing Noah's descendants to be able to migrate across China, across the Bering Strait, and down through the Americas. That's where we believe the Indians in North and South America may have come from. There were other ways they could have gotten here as well, but that's one of the possibilities. Northern Europe and Asia were covered with a large ice sheet. England was covered with ice. Particularly Denmark, Finland, Sweden, and Northern Asia was all covered with ice. The only residual ice of that whole area is Greenland today. Now, the reason that Greenland is still covered with ice today, it turns out it's kind of a unique location relative to the mid-ocean ridges and the heat that was produced by that, and this open water here that allowed the water to evaporate and be transported and precipitated on Greenland. I'm going to show you some pictures in a little bit that even emphasize that more. So and one of the reasons for the distinctive shapes of these is, and that there's no ice sheet down in Asia, even though it's very cold in Central Asia, there's not ice as far south as there is in the North American continent because there's not any near access to large body of water. It has to have moisture to be able to produce that. There's a lot more I could say, but I'm going to have to go on. I would also say that in the southern hemisphere, the whole situation is different because the Antarctica is centered on the South Pole. Here in the northern hemisphere, there's an Arctic Ocean with no continent there at the North Pole. In the southern hemisphere, the continent is centered on the South Pole, and it still has its ice sheet today. There's over 2 miles of ice still on Antarctica today, and it hasn't gone away. At the deglaciation, both Greenland retained their ice sheet and Antarctica because they still had a source of water to keep that maintained, whereas the one in Canada and Asia went away. And many of the glaciers in the mountains melted back up to higher elevations where it's colder. Well, there's a number of theories for forming ice ages. Basically, they fall into 2 categories, even though there's as many as over 60 different theories have been suggested. The terrestrial ice ages and the extraterrestrial ice ages. Extraterrestrials were produced by these space aliens. No. Terrestrial means it occurred by some cause here on the Earth. The extraterrestrial, which we'll get to in a moment, was by some cause outside the Earth, extra-Earth, okay? One which you may recognize having to do with our greenhouse effect that's suggested today, is a decrease in carbon dioxide. Today we're worried about carbon dioxide increasing, causing more greenhouse effect and our climate warming. Well, there seems to be evidence that during the Ice Age that there was a decrease in carbon dioxide. Now, it probably wasn't the cause of the Ice Age, as some have suggested, because the decrease in carbon dioxide actually occurred following the initiation of the Ice Age. It seems to have occurred later. So it seems to be a consequence rather than a cause. But that's a legitimate issue. Another one might be an increase in volcanic dust. If you had volcanoes going off, or meteorites for that matter, striking the Earth and throwing up all kinds of dust and forming fires and smoke, that would reduce the amount of heating on the Earth. For example, particulates in the atmosphere are great at radiating out heat to space. You know, when we had some of the volcanoes that went off here in the last few years, they produced cooling of 2 or 3 degrees for several years following the volcanic eruption. Well, you can imagine volcanoes all over the Earth, what it might do. Another one is this ice-free Arctic. It's possible that when the Arctic is open and not covered with ice, that water is free to evaporate more freely into the atmosphere and produce more snow to produce the ice sheets. And it's been suggested that that Arctic Ocean has been open and closed to flow through the Bering Strait and through the other side from time to time. And during the time it's closed, that water cools more, forms an ice sheet, and shuts things down. When it's open, it can form more ice and snow. And then in the southern hemisphere, it's even suggested that the surging of the Antarctic ice, which we've heard stories about, sometime within the next 100 years, a massive chunk of ice is likely to slide off of that continent into the ocean, break up as icebergs, and distribute throughout the southern hemisphere, changing the radiation balance dramatically, possibly leading to another ice age. That's one of the theories that's suggested. Well, none of these are really fully accepted because they don't have the periodicity that they're looking for, which is based on seafloor sediment data. And I'm not going to get into that, but that's the reason for it. Let's talk a moment about the extraterrestrial theories. For example, it's been suggested that the sun is not constant, that it could decrease its radiation. And in the past, we know that the sunspot activity was much greater than it is today. And that seems to have cycles to it, not only the 11 or the 22-year sunspot cycle, but even longer periods. There was what's called the Maunder minimum a number of years ago, and there seems to be some variations with sunspots. Could there be other variations in the activity of the sun that can change the radiation output? Most people say that's not, at least in the historical past, that's not been sufficient to explain an ice age. However, they are going back to that a little bit more these days again. Maybe there was a galactic dust cloud. As the solar system, the entire solar system moves through our galaxy, there are places where it's dustier than in other places. Is it possible that our solar system, as it moved through a particular place where it was dusty, that would cause dust between the sun and the Earth and cut down on the radiation coming to the Earth? That hasn't been fully accepted. And I did mention meteoritic bombardment, which actually I shouldn't have said with volcanoes because volcanic was terrestrial. Meteoritic bombardment would be extraterrestrial. And you can use the same argument like I did with volcanoes. If you had meteors coming from outer space, striking the Earth, throwing up a lot of dust, it would produce cooling. But the one that's generally accepted as the best explanation today is the astronomical theory. It's also called the Milankovitch theory. And it's basically the idea that there are some parameters in the orbit of the Earth around the sun that change on a periodic basis. And the reason they're looking for the periodic function is because in looking at seafloor sediments and interpreting the seafloor sediments in terms of a long Earth evolutionary time frame, they find 20,000, 40,000, and 100,000 year periods in the seafloor sediment that they believe can be associated with the orbital parameters of the Earth revolving around the sun. One of these is that the axis of the Earth tends to wobble. Another is that the Earth, in its elliptic orbit around the sun, goes from a circular to an elliptic orbit with a certain period. And then there's another one in which the elliptical orbit rotates. Each of those have its own period. They found some relatively good association with the seafloor sediment data for the 20,000 and the 40,000 year periods, but they can't find a good association with the 100,000 year period that they're looking for. The ice age, what they're suggesting is that there was multiple ice ages, as many as 50 or 100 ice ages in the historical past on the Earth, separated by about 100,000 years. In interpreting the data from the ice cores and the seafloor sediment, they believe that the ice sheets wane and grow with periods of about 100,000 years. So therefore, there should be an orbital parameter that would fit that, and there should be a good connection. Well, the 100,000 year one, they can't get this connection. In fact, it's so weak that nobody can convince themselves that it would do it unless there was some kind of a massive feedback mechanism. And this feedback mechanism, they don't know what it is. They haven't even suggested what the process could be, but their attitude is it has to be there. This must be the answer. So there's millions of dollars in conventional science spent each year trying to get a good explanation of the astronomical theory and bolstering it up. I don't know how many more years that's going to go before they give it up, but that's what's being done. Now, the thing that's interesting is this is the connection back to the greenhouse issue, because if there is this periodicity and it's associated with the orbital parameters of the Earth, then we're likely to have another ice age. And they've also found in looking at these studies, as you get closer and closer to an ice age, you have all kinds of instabilities and little amplitudes that crop up in a second order system, mathematical system. There are instabilities, and any little upset is likely to kick it off and cause the thing to go to one extreme or the other. That's why you hear such things as we're about to go into another ice age, or the greenhouse effect is going to take over and we're going to all get cooked, or the oceans are going to rise because all the ice sheets are going to melt. It all comes back to this interpretation of the age of the Earth and the seafloor sediments and this periodicity that's coming in and trying to explain the ice age. Now, in my opinion, that's completely the wrong answer. They're looking at a uniformitarian view of trying to explain this issue. And I think there's a much more straightforward explanation, and that's the Genesis flood. They can't find a strong signal to tie this effect to, when in fact the Genesis flood was a massive catastrophic event that produces all the energy you need to be able to explain an ice age. And I'll try to help you understand that in a moment here. There are two basic requirements for an ice age. One is you have to have more snow, but maybe not a lot more snow. Maybe you just have to have it continuous all year round, but more importantly, you don't want to melt it during the summer. Can you imagine if you had the same amount of snow we had right now, but it just never went away in the summertime, it just kept accumulating? It wouldn't take many years to be able to have an ice sheet or a glacier or a new ice age. Well, that's the basic idea, and there's been a number of people who tried to model that. One of the basic problems is that the way in which water vapor in the atmosphere is held is a function of temperature. Here is temperature along the x-axis in degrees centigrade. At 0, that's freezing, and the warmer temperature, you'll notice that and the vertical axis is what's called the saturation vapor pressure. The higher that number, the more water vapor you can hold in air. So that the warmer the temperature, the more water vapor you can hold in the air. Therefore, you have more water vapor to condense out someplace else as snow. So the basic issue is that if the air is too cold, you can't get very much water vapor, therefore you're not going to get much precipitation. Many of you that live in northern climates have probably heard the old adage, it's too cold to snow. That's literally true. If you have a very cold air mass that comes down from Canada and it's extremely cold, it can't hold much water vapor, so you find just little bitty snowflakes or ice crystals, and they don't lump together and they don't accumulate much. So it has to be relatively warm in order to snow. That kind of sounds silly, doesn't it? But you have to have warm locations where water vapor can be evaporated, and then colder locations where it can be condensed out. Now this ice age has been attempted to be modeled by a number of people, and no one, using uniformitarian assumptions, which means basically the conditions as we observe today, very little change, can model it. Here's an example of the boundary of the ice sheet that we know occurred up in Canada now from the evidence. That's as far as models have been able to show it coming southward in the North American Peninsula, North American Peninsula, down to about Hudson Bay. Well, we know that that permanent ice sheet went clear on down into central Midwest here. And no model has been able to explain how this whole portion here would have been covered with ice and snow with uniformitarian assumptions. Mike Ord, who is here, and many of you know, has made this statement in his monograph, The Ice Age and the Genesis Flood, which you'll find on the back table or in the bookstore. In summary, the proposed solutions for the Ice Age can't provide the sustained cooling and the heavy snow needed to glaciate northeastern North America under essentially uniformitarian conditions. Okay, you can't do it with the conditions we see today. Everybody's tried and you can't do it. But we believe a biblical model brings into play a lot of these issues that they've explored individually, such as volcanic dust. Volcanoes were going off like crazy during the flood and following. More cloudiness. It rained for 40 days and 40 nights, and there was probably clouds all over lots of places on the earth for many years following, particularly in the polar regions and in the tropical regions. There were barren land surfaces. There was more snow cover, which produces cooling. Variations in carbon dioxide, something we call fixed storm tracks, and high ocean evaporation. This bottom one down here, high ocean evaporation being the primary effect. Okay, let me just point out something that you may not be aware of, and that's something called the mid-ocean ridges. We didn't know this until the 60s, when we were able to start taking measurements through the depth of the ocean. But if you look on the bottom of the ocean, you'll find something called ridges, mid-ocean ridges, that are made up of basalt. The Earth, at some point in its history, and we believe this was during the flood and shortly following, the surface of the Earth was cracked open and magma, or basalt, came up from the mantle into the bottom of the ocean and formed these ridges. Like here's one that runs down from near Iceland, just on the south side of Greenland, down through the North Atlantic, down through the south, went around Africa into the Indian Ocean, and comes out over here south of Australia and around up through the Pacific Ocean and bumps into the Baja near Southern California, right near my home, right there. At any rate, this formed at some time in the past. The conventional view is that the basalt came out very slowly over maybe 100 million years or more, spread out on the bottom of the ocean, and they agree that these continents were separated apart as part of this process, and many of the continents were moved around. But over millions and millions of years, we believe in a biblical model this happened very rapidly during the year of the flood, or somewhat following, very rapidly. So basically what I'm suggesting here, and the group that presented a paper at the ICC about 8 years ago, it was called the catastrophic plate tectonics model. Now that's still somewhat controversial with many, but basically the idea was that the tectonics that is talked about in conventional science didn't happen over 100 million years, it happened in the year of the flood. If that was the case, all of this basalt, and by the way, this mountain chain is 40,000 miles long, some 6,000 or so feet high in the highest spots, and several hundred miles wide over the floor of the ocean. Completely basalt, so it was hot when it came out, and that heat would have been absorbed into the ocean and would have been there at the end of the flood. Plus all the other processes, all the other geologic work that had to be done, moving continents around and so on. So you can imagine how hot the ocean would have been left. Here's a picture of the island of Surtsey when it formed up near Iceland. I mean, this is lava intersecting the ocean water, producing tremendous quantities of steam, and actually throwing lava into the air, as you can see here. Some of you may have been to the large island of Hawaii and seen the lava coming off there and into the ocean. It produces these beautiful pink clouds at night and steam and everything. That's just a little minor thing. It wasn't very explosive, didn't cover a lot of area, but we're talking about a 40,000 mile long mountain chain that did this within probably a year's time. Well, with all this hot water around, you can imagine what would happen. I'm suggesting, and I'll show you in a moment, hurricanes would have formed, I believe, and a lot of cloudiness. Now, the Bible says that it rained for 40 days and 40 nights, and that was over the entire earth. But I believe that it probably continued to precipitate, particularly in the form of ice and snow, in the polar regions and on mountaintops for many, many years after that. That's where the ice sheets would have come from during the Ice Age. So you would have had a lot of clouds, which would have also reflected a lot of radiation back to space. You would have also had barren land. This is what it looked like when Noah got off the ark. We had this picture taken from the front door of the ark as Noah was about to descend into the new world. Actually, this is on Mars. But this is what the earth probably looked like at the end of the flood. Have you ever thought about that? I mean, the whole earth was devastated. There was no trees, no grass. I mean, it was just barren. This kind of barren condition would be as if you had a desert over the whole earth. The radiation conditions would have been completely changed by this, and tremendous quantities of radiation would have been reflected right back to space. So temperatures would have been much colder on the continent than they are today. Over the ocean, it would have been still warm because of all that heat in the water. So snow cover, as it began to form in the polar regions and slowly expand southward to cover larger and larger areas, would have also reflected a lot of heat back to space in the daytime. At night, the infrared radiation would have been tremendous. If you've ever gone skiing, you know that you get sunburn on the bottom of your chin very easily when you're snow skiing. Well, that's the reflection of solar radiation from the surface of the snow. But at night, it gets very cold on a snow surface when there's no clouds above because the snow is like a black body. It irradiates infrared radiation to space extremely effectively. So there's all kinds of heat that would escape from the Earth into those conditions. Measurements in the ice cores and ice pits that we measure in Greenland and Antarctica show that carbon dioxide concentrations were considerably lower during the ice age than they are today. That would have caused a reduced greenhouse effect, causing it to be colder. There also, from the modeling that we've done, it indicates that the continents would be relatively cold inland, interior, and with the warm water out in the oceans, you would have gradients of temperature from the continents toward the ocean. In other words, it would get cold here and very warm toward the ocean. This produces an effect in the motion of winds called the thermal wind, which causes storms to move along parallel to that, or perpendicular to that gradient. And such things as nor'easters, which tend to form on the East Coast, would want to move right up along the coast, and they would want to do this day after day. Probably not just in the winter, but all year round. So some of these can accumulate 1 to 3 feet of snow in each storm. If you had one every 3 days all year long, you got 100 storms. There's 300 feet of snow in one winter or 1 year. It's going to, of course, it's going to compress, but it's going to accumulate pretty rapidly. Here's how it works. If you look through a cross section looking north, you got the warm ocean off the coast, you got the cold land, and you got circulation bringing at low levels in the atmosphere, bringing that warm, moist air off the ocean over the continents and dumping it out as snow. Okay, here's an example of a case just recently that illustrates this on Greenland. In 1945, there was a squadron of airplanes, P-38s, you know, the twin-tail fighter plane that we had during the Second World War. There was a squadron of those, and I think 1 or 2 B-17s that were on their way to England right near the end of the war. And they got out in the Atlantic, and as they radioed ahead, they found out that all the fields in England were shut down due to fog. So they turned back and headed back toward the East Coast, and they hadn't gotten turned around good, but they found out that all the airports, fields on the East Coast of the United States had closed down with fog. They had no place to land. Those days, their systems weren't very good for landing in fog, and navigation wasn't very good either, so they kind of circled for a little while trying to figure out what to do, and they realized they didn't have enough fuel to go anywhere now. So they ended up going and landing on the southern coast of Greenland. And they actually landed safely. They put their wheels up and belly landed. One of the P-38s ended up flipping over, and one of the pilots had a broken arm, but everybody else landed safely. And about a week later, they were rescued. But their planes were left there, and over time, they were slowly covered over with snow and ice. Well, a fellow by the name of Pat Epps from Houston, Texas, heard about this, and he decided, I'm going to go look for those planes and recover them, because they're very valuable now. So he went and put out an expedition, and they went to look for these planes, and they couldn't find them. They had metal detecting equipment and so on, but the reason they couldn't find them was because they were so deep down in the snow and ice at this point. It turns out in that particular coast of Greenland, the snow accumulates at the rate of about 5 feet per winter. And so that was about 50 years before when those planes went down. That was 250 feet of snow and ice. The planes had been buried down 250 feet. Well, they finally located them by metal detection, And they decided, well, we got to build some kind of special equipment to go after these planes. And so they designed what they call the gopher. It was a conical shaped thing. You're looking up out of a hole up toward this conical shaped thing. The point's right here in the middle. And they surrounded it with copper tubing, and they pumped hot water and steam through this, and they just sat it down on the snow and let it eat its way down through the snow. Here you can see 4 pits that it made these round things here are the pits that it melted its way down through, and then they dug out the intermediate ice and snow in between, 250 feet down, and they found the P-38. They took their steam equipment down there and melted the snow all around it, and then they found that the planes were very lightly damaged. They took them apart, winched them back out of the hole, hauled this one back to Houston and repaired it, and it's flying today. Now you believe that? A lot of money for that, but that's what they're doing. But they're thinking about going back and trying to recover the other planes. Now, the reason the whole point of this is that there was 250 feet of ice and snow there. Why is there so much snow there? Well, it turns out, how many have heard of the Gulf Stream? You know, it's this kind of river of warm air that comes up out of the Gulf of Mexico, goes up the east coast, across the Atlantic Ocean, right around the southern tip of Greenland, actually goes over and bumps into England. Near Land's End, or on the Cornish coast in England, there's actually palm trees out in the southwestern corner of England because the Gulf Stream interacts right. It's a great resort area. You ought to go there sometime. I'm thinking about it. At any rate, that stream is warm coming up right next to this very cold coast of Greenland. So you got the warm water, and it's not a real big river of water. It's, I don't know, maybe 100 miles wide at the most, but that water is being evaporated out of the ocean there, brought over onto Greenland and dumped as snow. Now, think of the oceans over the entire world being warm like that, and the conditions where you could dump that snow on the continents. It can happen very, very quickly. And you can get, in fact, the modeling that we've done shows that you could accumulate the snow and ice up to a mile deep in Greenland in less than 500 years. Well, that's what we need for the biblical model, right? Actually using the conventional models that are used by the standard atmospheric science community with a warm ocean surface, you can get enough snow and ice to explain the ice age in 500 years or so. Okay, anyway, basically this discussion will explain the extensive ice sheets that we believe covered the Earth and glaciers in the past. It's pointed out major problems in the conventional models because they're assuming uniformitarian conditions. We need a catastrophic model to be able to explain the ice age, and we believe that the biblical model fits this very well. This is the creationist opportunity to really show our stuff, to be able to come up with a solution that can be supported and justified and points to the Bible as the explanation. Isn't that a neat solution? Okay, I got to show you some really neat images here. One of the things I said, if you have a warm ocean, you're likely to have hypercanes. Hypercanes are these really gigantic, massive hurricanes. By the way, this is Hurricane Gladys back in 1968, I believe it was, taken from one of the Apollo ships. Here's Hurricane Dennis in 1999. This is just a little segment of it showing it in motion, where we use a program called Viz 5D, where you can actually take the data and display it in perspective in an animated form. Now, that's just one short segment that we have. In fact, in the book, I'll sell my book at this point. In the book that I have on the table back there, the monograph called Climates Before and After the Genesis Flood, this segment plus 3 others for Hurricane Dennis are on the CD in the back of that book that you can play on your own PC. Use it as a screensaver. Probably use up most of your memory, but you could do that. There's a lot of other hurricanes in there, plus some of the simulations that I've done. That's what I want to show you next here. This is Hurricane Florence that my student used. It was a small hurricane back in 1988 that was in the Gulf of Mexico. Here's the position as it came up through the Gulf of Mexico, and it never really developed into much of a hurricane. It was just a real small hurricane, and when it hit the coast, it died out very quickly. But we had the data for this that we could simulate in our modeling, and what we did was we took this hurricane, changed the surface conditions so the temperatures were very warm in this boxed area here, and then allowed it to grow and see what it would do. it grew like gangbusters, and it formed an anvil that started out this size right here, and each one of these little contours is 1 hour later. So after 16 hours, the anvil from that hurricane, not only did the hurricane cover the whole Gulf of Mexico, the anvil covered all the southeastern United States, most of Mexico, and most of the Caribbean. So I mean, we're talking about a giant hurricane. Here's the size of it, the average anvil in its area in square kilometers as a function of time from 0 to 16 hours. It went very dramatically larger. Here's some winds at about 5,000 feet above the ocean, 850 millibars for those of you that know that lingo. These little white arrows here, which you can't see real well, at 6 hours into the simulation and then 12 hours into the simulation, it really began to gear up and really got strong. Here's the vorticity of that hurricane, which is a measure of the motion in a circle. Best way I can say that, as a function of time. This is about the place where it hit the coast and then died out. It was really getting strong and then died out. Here is a simulation of the hurricane in 3 dimensions. And what I'm going to display here is the cloud water content in yellow and the rainwater content in green. This is the Mexico here, the Rocky Mountains, the Gulf of Mexico is under here. This area that's kind of squarish in yellow, that's where we increased the temperature. And the temperature for this particular simulation was at 45 degrees centigrade. That's about 120 degrees Fahrenheit, very warm. And this thing just grew like gangbusters. And this is with a standard mesoscale meteorology model, it's called, MM5, from the National Center for Atmospheric Research that you can run on a personal computer with the Linux operating system. And as I said, the yellow is cloud water content and the green is rainwater content. So these are shafts of rain falling out. And you'll notice it's beginning to get to classical hurricane shape, and it rotates in a counterclockwise direction as you look down on it. Now, this hurricane, this is the hypercane. The real Hurricane Florence had winds up to about 100 miles an hour in the horizontal maximum. Hypercane Florence went up to over 300 miles an hour and would have gone a lot higher if it had not run into the coast of Louisiana. The vertical wind speeds were on the order of 30 to 40 miles an hour in the hurricane and exceeded 100 miles an hour in the vertical over in the hypercane. The precipitation rate was 10 times greater in the hypercane than we had in Hurricane Florence. It was 10 inches per hour is what it did during the hypercane. So we're talking about a giant storm. And I'm suggesting that because of the sea surface temperature globally, you could have had these kind of hypercanes in many places over the earth coming onto the continents and dumping massive quantities of water and rain, eroding the unconsolidated surfaces, and wind damage of unbelievable proportions. So, and that would have gone on while the ocean surface was relatively warm. Anything above about 30 or 40 degrees centigrade, which is maybe 90 to 100 degrees, which only happens near the equator today at the end of the summer heating season for short periods of time. And they don't grow that big because it isn't that warm and isn't warm for very long. Okay, so let me conclude from that. Hypercanes have been successfully modeled by MM5, this mesoscale meteorology model. The high surface temperatures form hypercanes, and these kind of hypercanes, we've been able to demonstrate that they quadruple the horizontal wind speed, they double the vertical wind speed, they increase the precipitation tenfold, and I'm suggesting there were probably many hypercanes likely after the flood, and incredible erosion was likely because of them. Okay, that was a quick treatment of the vapor canopy, the ice age, and hypercanes. I'm sorry I couldn't get to some of the other topics, but maybe on the side, if you're interested, I'll try to talk with you more about those. Thank you very much for your attention.